Hi everyone, this is going to be our note for 7.5, and it's going to be split up into two videos. The first part of the video is kind of an investigation where we're just going to get used to graphing and looking at exponential functions. So to kind of start us off, we're going to look at this example, which I'm sure you've seen something similar to this before. You have a job, it doesn't matter what the job is, and you can get paid in two ways. You can get paid either $1 million for 30 days in total of work, or you can be paid 1 cent on the first day, and then every day after that it doubles. So if you get paid 1 cent on the first day, on the second day it gets doubled to 2 cents, and 4 cents, and so on. So which one do you prefer and why? Take your guess and you can write it right here. But we're actually going to do this on our table right now. So we can start with $0.01, and then that would be doubled 2 cents, and then so on. So why don't you fill in the table, and then we'll compare answers after. Okay, so you probably got these as your numbers, hopefully. If not, double check. Now you may be wondering, well, how did you get these numbers, not the other numbers in between? Well, there is an equation we can use to help us get that, but okay. Alright, here are the other values in case you wanted to double check your answers for the other values. But again, we have an equation to kind of figure out what these numbers would be. But first, let's answer some of these questions. What did you notice about the continuous two y values? And this means, what do we notice about like any two successive ones? So if like I have like 0.08 and 0.016. And what do we notice about maybe 1.28 and 2.56? Or any kind of consecutive one, any pair of these that are right beside each other. So let's say these two as well. What pattern do we notice between these two y values? Well, if I, whatever it is, if I got the upper one, like in this case 16 and 15, so 327.68 over 163.84. If I divide those two numbers, and I know the answer, but I'm just going to double check on my calculator anyway because, you know, why not? And if I divide them, I get 2. And if I did that for 8 and 9 here, if I divided these two together, I would get 2. So what did we notice about the continuous two y values? They divide to give 2. Or we can say that they have a ratio that gives 2. Because it's always doubling, which makes sense because that's why we're saying it doubles every time. So we can make a formula from this now. So let's say the payment we would get, let's say, and I'm just going to tell you the formula because this makes it faster. Because we have our ratio of 2 here, it's going to be 2 to the power of whatever the number of days it is. The number of days here. It's going to be to the power of n. And we're just going to multiply that by our initial amount, which is going to be 0.01, because we start with 1 cent. So we can use this formula to help us calculate the payment we would get for those days. Sorry, I just wanted to add to this question here that they divide to give 2. I want to put that this is a constant ratio, meaning it doesn't matter which 2 I pick. When I divide the higher one by the lower one, it's a constant ratio of always going to get, we're always going to get 2. Sorry, back to our equation. Payment is equal to 0.01 times 2 to the power of n. Where's the variable? Well, it's on the exponent. And is this a function? So remember our definition. We could use the vertical line test, but we haven't really graphed this yet. But our other definition of a function is for every x value, there's only one y value. So I'd say in all of these cases, I don't think we're ever going to have an x value where there's a repeating y value. Meaning on day 3, it's not going to be 2 different prices. So for every x value, there is one y value. So I'd say that yes, this is a function. Now, for the sake of this scenario, you can see that, you know, by the end of this day 30, we have 5 million. And if you're getting paid this much every day, well, you're getting a lot more money than the first scenario. So scenario B is the best. Alright, for the next part of the video, we're going to be just graphing an exponential function. So any exponential function is in the form f at x equals b to the power of x, where b is greater than 0 and the variable is in the exponent. So we're just going to start with f at x is equal to 2 to the power of x, and we're going to choose some positive x values and some negative x values to see if we can notice any patterns. So why don't you pause the video, fill this out, and then unpause and you can check your answer with me. So here are the values if you want to double check your answers. Just note for the negative exponent parts, remember for these negative x values, if I have a negative exponent, to get rid of that negative exponent, I move it to the bottom of a fraction. So it becomes 1 over 2 to the power of 2, which is 1 over 4, and then we divide to get these decimals. And well, we can see some patterns right now. What happens to the value of 2 to the power of x as the value of x gets very large? So if these exponents and the x values, if this became like 2 to the power of 30, 2 to the power of 40, 2 to the power of 50, what's happening to these numbers every time? Well, we can say the value gets larger. But the word is exponentially larger, which is where we get our name exponential. But we can also say it moves or goes to infinity. One of our math terms now. I think some people know that this is a symbol for infinity. What this means is if we just continue this, then this will just keep going on in the positive direction forever. So infinity is not a number, just a concept to let us know that it's going to go on forever in this direction, always going towards infinity. You can even designate positive infinity. There are cases where if it's going down to a negative number, we can say negative infinity. But in this case, it's going to go towards positive infinity. It's going to go upwards no matter what. Now, what happens to the value of 2 to the power of x as the value of x gets very small? Meaning if this went to 2 to the power of negative 40, 2 to the power of negative 50, 2 to the power of negative 100. Well, every time it just seems like I'm adding more and more zeros. So we're not getting towards a negative number. If this just keeps going towards how many zeros do we need to get to, let's say 9 here, it seems like this is always going towards the number 0. So we can say the value moves or gets closer to 0. I'm just putting here, but it's not actually reaching 0. Meaning no matter what this negative x value is, 2 to the power of negative 2 million, it's still just going to be a lot of zeros and then some other number at the end. So it's never actually going to reach 0. It's just always going to be moving towards it closer and closer and closer. So that's a pattern that we can see for these exponential functions. So next we're just going to graph it. If you want to look down here, you can try graphing it, and then we're going to go over these questions too. Okay, so these are my points. You could use Desmos as well. Sorry, I should have mentioned that before. You can use Desmos if you want to just type in your equation as 2 to the power of x. But if we put those values in of just 1, 2, 3, 4, 5, 6 even, put them in at 2 to the power of 0 is equal to 1, 2 to the power of 1 is 2, and so on. If I join these points on the positive, we notice that these numbers just get these increase very quickly. So at 6, it's at 64, which is way off where our range is. So I'm just going to make it go up here. So this is what I meant before with infinity. It's going toward infinity. It's going towards some positive value forever. It goes on forever, so we say it goes towards infinity. Now on the other end, on the negative side, if we have negative x values or negative exponents, we just see that it's always going towards, again, 0, never actually reaching 0. So this will always just go towards 0 like that. So to answer these questions now, is the graph an increasing or decreasing function? This means if I move from left to right, meaning if my x values are increasing, going from the negative direction to the positive direction, left to right, increasing functions go up and decreasing functions go down. So from left to right, if the y values increase, then we have an increasing function, and if they were to go downwards, we'd have a decreasing function. So in this case, if I go from left to right, my lines go up, So we have an increasing function. Just put increasing here. All right, increasing function. Will the value of 2 to the power of x ever equal 0? And we just seen here on the graph, you can check on Desmos as well, and we saw when we did our calculations here, if this is even 2 to the power of a big negative exponent, we're always going to get 0, so it's never going to actually reach 0 though. So no, it will never equal 0. Are there any values of x that would make 2 to the power of x undefined? Explain. So are there any x values that you can think of in the positive or negative direction that is going to make this not a function anymore, or make it where it's undefined, where there's like an asymptote or something? And I would say no, because whatever x value I can put in there, I always get something. I always get some y value. What is the y-intercept? That occurs when x is equal to 0. So 2 to the power of 0 is equal to 1. So the y-intercept equals 0, 1. The domain, well, the domain is if it's any x value exists, we can say that x is going to be any real number against brackets, because again, in either direction, any negative x values is going to give us a number closer to 0, and anything in the positive direction just goes towards infinity, a bigger and bigger number every time. So x is any real number, and the range, you can say y is any real number, but we have some restrictions here, and that y has to be greater than, all the y values are always greater than 0, because we don't have any negative y values. Keep in mind, it's not y is greater than or equal to 0. There's no equal sign there, because y is never going to be 0. It's never going to reach the 0, so it cannot be equal to 0. So the y values are always greater than 0. So those are some properties of this exponential function. All right, we're going to do this again, but now we're going to have, instead of 2 to the power of x, we're going to have half to the power of x, and we're going to choose some positive x values here and some negative x values here. I think I forgot the negatives in the note, so just add the negatives here. And then we'll do this a bit quicker because I think we're starting to see some patterns, and I won't have to explain as much. So fill this out and then unpause the video and you can check your answers with me. All right, so these are our numbers. I'm just going to do one of these to show you what's going on here. If I have 0.5, I'm going to do it for half though. Let's say the power of, oops. Let's say half to the power of 5. Remember my exponent rule here, where I'm going to apply this to the top and the bottom. 1 to the power of 5 is 1. 2 to the power of 5 is 32. And that's how I get my decimal. And sorry, for the negative exponents here, if I have half to the power of, say, negative 5, well, if I apply that now to the top and the bottom, according to exponent laws, if I want to change the sign of them, I just flip them. So this will become 2 to the power of 5 on the top and 1 to the power of 5 on the bottom. Sorry about that, my phone went off. So you get 32, because 1 to the power of 5 is just 32 over 1. So we kind of get the opposite thing happening here. So that's what we're going to say in our boxes here. So what happens to the value of 0.5 to the power of x as the value of x gets very large? We can say that this value, as the x values get bigger and bigger and bigger, gets closer and closer to 0. So the value gets closer to 0. But again, not reaching it. Not reaching 0. And what happens to the negative x values? As x values get very small in the negative, or get very small in the negative direction, then we get the value gets larger. And we see that it's also going towards infinity and positive infinity because it's going towards larger and larger positive numbers. So let's now graph this. You can use decimals again if you want to, or just graph this with some values on your calculator, and then we'll answer the questions. So here's your graph. Should look like this, and it should just kind of look like the opposite of the other graph. Here's the other graph right here. Together they're kind of, okay, never mind what it looks like together, but it looks like just the opposite of this graph. So is the graph an increasing or decreasing function? So I drew that, I didn't draw it, but like I did this with my pencil to show decreasing function. That's not a decreasing function. This is a decreasing function, meaning as I go from left to right here, my y values are decreasing. They're getting smaller and smaller and smaller, and they're going to keep getting smaller until they get to, well, but never reaching 0. So this is a decreasing function. I guess this can be a decreasing function. I'll have to worry about that later. Will the value of 0.5 to the power of x ever equal 0? And just like the other function, whatever x value I can think of to put in here, any one of these x values, or anything larger or smaller in the negative direction, answer is no. It'll always be going towards 0, but never equal to 0. Are there any values that would make this undefined? Nope, because we can put any x value here, and we'll get a corresponding y value. What's the y-intercept? Same as before, we said x equal to 0, which is equal to 1, so 0, 1. The domain, well, x is any real number. And the range is also the same, in that y is any real number, but y still has to be greater than 0, because it never reaches 0 and it never gets to any negative values for y. So now let's compare how did the graph of 2 to the power of x compare with the graph of 0.5 to the power of x. We're going to talk about the similarities and differences, and we're really just looking at, well, what if the b value in our exponential equation, so the base here, what if it's greater than 1, and what if it's between 0 and 1 or a fraction. So similarities, well, both of these have the same domain and the same range, the same y-intercept. And I guess you could say that they're both, functions if you just wanted to be technical. They both have one x to one y value, so those are the similarities. The differences is that when b is greater than 1, so like 2 or 3 or more, then it's going to be an increasing function. And when the b value, or the base, is a fraction or a decimal, then it's going to be a decreasing function. And just to go back to finalize this, that this is a decreasing function, this is also a decreasing function, which is the motion I made before. So sorry for that confusing part, but that's not really relevant to this part. But so this is the important part. These are the similarities and differences between having a base that's a fraction and having a base that's greater than 1. Alright, so to kind of apply everything we've kind of put together, we just have this final page of just kind of a quick summary. And we're going to look at this rate of change and just kind of apply what we've seen and see if we can apply it to the scenario. So the rate of change for any graph shows how quickly the graph increases or decreases. And we've been doing kind of rate of change stuff for quite a while. So for like linear relations, this is like y equals mx plus b. When we had this, we did rate of change. We did things like first differences. We saw that they have a constant rate of change. Those first differences were the same. And that was actually the slope, which was m. For quadratic relations, they have a predictable rate of change given by a step pattern of a function. So like we had going over 1 up 1 and then over 2 up 4, that kind of step pattern. This for parabola. You'd also say with the second differences that they were constant, so that's how we knew that they were going to be a quadratic relation. For exponential relations, they have a rate of change that is proportional to its value at every given time. That's when we did our ratios, when we divide the upper number by the lower number, and those ratios should be the same for exponential relations. So let's consider the following four equations here, A, B, C, and D, and the four graphs. So these are the equations, these are the graphs. Identify which graph represents each exponential relation. If you're not sure, take a guess, and then unpause, we'll take it up. Alright, so these are my answers. So how did I get to these answers? Well, I know the first two, y equals 2 to the power of x and y equals 5 to the power of x, those have a base that is greater than 1, so I know it's going to be increasing. I know it has to be c or d. So then I just put x is equal to 1 for a positive x value, and when x is equal to 1 here, y is equal to 2. So I just saw where does y equal 2. That happens for line D, which is this one. And for C, when x is equal to 1, the y value is equal to 5. That is here, so C has to equal 5. Then I did the same thing for these two. I know these are decreasing because they're fraction as the base, and I picked x equals -1. If I put -1 here, remember it goes to the bottom, and then I flip it to make it a positive number, so this would be at -1, y is equal to 2. That's over here for line A, and then 5 for B. So that's how I got my answers. So what does each of the exponential relations have in common? Well, they all have this y-intercept in common of 0, 1. Which graphs show growth or an increasing relationship? This is C and D. And which ones show decay? Well, that would be A and B. Decay means decreasing. Now to summarize all of these things, we can say when f at x is equal to 2 to the power of x, we have an increasing function. And this also applies to all exponential functions. So when b is greater than 1, we always have an increasing function. And when it's a fraction, in this case, or 0.5 like we did, it is a decreasing function. The y-intercept all the time, no matter what, 0, 1. The domain for both of these was x is any real number. And then our range is y is any real number, but y has to be greater than 0. So I'm just going to write this a few more times. Thrilling video, I know. I was doing pretty good without. There we go. One more time. So these seem to be consistent patterns, and these are some patterns for our exponential function. So it was a kind of a long investigation, but hopefully we understand these similarities and differences. Just to give you some scenarios where we see this, like we saw this before in the very first example with the money. So in your finances, we could see exponential growth or decay. I mean, if your business is doubling money every year or every month, every month is really good, but every year is still amazing. So we can see that in finance. Alternatively, you could be losing money a lot very quickly, so we could see that being a bad thing as well. If you're taking, biology, you might know about invasive species, where, once a new species is from a different ecosystem is introduced somewhere else, and then it kind of grows out of control, meaning they breed very quickly, and then maybe their population increases very quickly and starts damaging or affecting the other organisms in that ecosystem. So these are a couple examples where we can see exponential functions. So thanks for your time.